This is the BBC.
This podcast is supported by advertising outside the UK.
Thanks for downloading the In Our Time podcast. For more details about In Our Time and for our terms of use, please go to bbc.co.uk/Radio4. I hope you enjoy the programme. Hello. In his poem Bright Star, John Keats wrote, "Bright star, would I was steadfast as thou art." For Keats, the stars were symbols of eternity. They were beautiful and ordered and unchanging. Modern astronomy tells a different story. Stars, like everything else in the universe, are subject to change. They're born among vast swirls of gas and dust, and they die in the stunning explosions we call supernovae. They create black holes and neutron stars, and in the very beginning of the universe, they forge the elements from which all life is made. But how do stars keep burning for millions of years? Why do they self-destruct with such ferocity? And what will happen to the universe when, or is it if, they all go out? With me to discuss the life cycle of stars is Paul Murdin, Senior Fellow at the Institute of Astronomy, Cambridge, Phil Charles, Professor of Astronomy at Southampton University, and Jana Levin, Advanced Fellow in the Department of Applied Mathematics and Theoretical Physics at the University of Cambridge. Paul Murdin, how many stars are there in the universe? What are we talking about?
Well, there's one star that's very special to us, the Sun, and all stars are suns like that. In the night sky, you can see maybe 5,000 stars, something like that. They look different from the Sun because they're so far away, but they're essentially the same. All of those stars and our Sun are members of a collection of stars called the Galaxy, the Milky Way Galaxy. And there are perhaps 30,000 million stars in the galaxy. And there is a spread of galaxies throughout the whole universe, perhaps as many galaxies in the universe as there are stars in our galaxy. So you're talking altogether in the universe of perhaps 10,000 million stars altogether. To put the number in context, it's something like as many stars in the universe as there are blades of grass on the world.
How do you imagine that, Paul? I mean, I see the figures, I've got notes from what you've written and so on, and I look at these 1,000 million stars. Just as a matter of interest, how do you get your head around that?
Only through the mathematics, only by writing down the numbers on a piece of paper and multiplying them. I think the difference between 10,000 million and 9,000 million is not that obvious, so it's what's written on the piece of paper. But the awe and wonder of these numbers is in every astronomer's mind. Stars were among the very first things created in the universe. Why do we think this? Well, astronomers have a tool which historians would die for. They travel in time. As they look further away in distance, the light from what they see, the light from distant stars, has taken a very long time to get to them. And so the light that we receive from a distant galaxy contains an image of that galaxy as it used to be a long time ago. And with the current big telescopes that we've got, space telescopes, huge, great ground-based telescopes and so on, we can see so far away that the light from those stars has taken perhaps 95% of the age of the universe to get here. So we can see those stars and galaxies as they were during the first 5% of the age of the universe. We can look back almost to the Big Bang.
It's extraordinary when you think of it, isn't it? It's like being able to look through a window and see the Battle of Hastings, that sort of thing. Jana Levin, stars don't live alone, but they come in massive groups called galaxies. Which came first, the galaxies or the stars?
That's also, I think, quite an active area of research. But the current story really starts with the Big Bang, when hydrogen is created, when the simple elements are created, and from this primordial kind of gas, a large clump will form eventually. And you could call that clump a kind of proto-galaxy. And in the core of it, you'll find something which starts to collapse eventually, forming possibly a supermassive star, a star that could be thousands of times the mass of the Sun, maybe hundreds, maybe thousands. And so, in a sense, those very first stars form coincident with the galaxies that are first forming in the early universe. Later, those proto-galaxies can begin to coalesce, forming larger galaxies. They can flatten out, forming kind of disks, and within those disks we have the more ordinary kinds of stars forming. So later on, ordinary stars like our own sun form in gas clouds in the disks of these galaxies.
Can you give us more detail? You say form. Mm-hmm. What does that, as it were, mean?
Well, it's quite amazing, really. You have this, what seems to be a kind of smooth background after the Big Bang. Everything was very, very hot and smoothed out over large scales and kind of cools down. And as it cools down, very small clumps that were present can begin to accrete matter gravitationally. So stuff becomes gravitationally bound, just the way the sun keeps planets in orbit around it. These clumps can start to keep matter, maybe not in orbit, but pull matter in towards it and accrete and get larger.
So the first activating force is gravity, sorry?
Yes, the first force is gravity. I mean, the most important force in these early phases is just the gravitational pull of matter on other matter. And as it begins to clump and condense, you form more massive objects that have even stronger gravitational pull. So they can accrete more and more matter, and you get larger structures forming.
Sorry, you were about to go.
Well, no, it's been debated for a long time whether these large structures break up into smaller structures or if it's hierarchical and small clumps then find each other and build up larger and larger galaxies. But that's the loose picture.
Phil Charles, what causes these protostars to ignite and become proper stars?
Well, Jan has been talking about these clouds that stars are formed out of, and they literally just collapse because of their own self-gravity, which is stronger at the center. And you have a protostar, which is the denser central region, and it is just a case of the central regions having to balance the force of gravity with something. Well, what does it balance it with? Is the material, the gas, has to have energy. As it collapses, it gets hotter, and that heat, as your compression, is what holds it up. But that heat eventually gets radiated away, and the cloud carries on collapsing down, getting smaller and smaller, but hotter and hotter, until eventually you need temperatures in the center of about 15 million degrees, when at that point you can switch on the central engine of all stars like our sun, in which nuclear reactions begin. You need very high temperatures because what's causing this is the essential material there is just hydrogen. It's not hydrogen atoms as we have on, as you know, on Earth, but the temperature is so high that the electron is stripped away from the hydrogen atom, and you just have the central nucleus, the proton. And if the temperature is high enough, then these protons can come close enough together to overcome their natural repulsion, and then they interact and they fuse. And this hydrogen fusion is something we've been trying to emulate on Earth with fusion reactors, not successfully yet, of course. But when that process turns on, the protostar becomes a star and it enters what we call the main sequence of burning.
Does anybody know why the pull of gravity is the pull of gravity in the first place? I mean, why Jan had described it these little lumps, these little things, the smooth surface that comes out of the Big Bang, but these little wrinkles, these little lumps, which begin to gather everything in because they have a slightly more dense and things are attracted to them. Where does that come from? Jana, do you want to
Yes, that's true. I mean, these are subtle questions. Why is gravity an attractive force is another way of asking a question. Why does gravitational pull between two massive objects cause them to come together, unlike two electric charges which might be repelled? Those aren't necessarily that easily understood, but Einstein's theory does give a very different picture than gravity as this kind of pulling force. In Einstein's theory, what he suggested was that what mass and energy do is they curve the fabric of space itself, so that when things are drawn together, they're following the natural curves in space that result from the presence of large mass and energy. And it's a very elegant picture. It would be great if we could fuse that with all the other forces to understand them in a way that made them all look very, very similar. We haven't quite gotten there.
Paul, do you have a view on this before I go back to Phil?
Well, to some extent, I think the answer is irrelevant. I'm less interested in what gravity is than what gravity does. I mean, gravity is, to some extent, gravity and general relativity and so on is a description of what happens. And so seeing the way in which things happen and relating them all together and getting a causal framework of that mapped out, let's call it general relativity, is the big achievement. Going below the surface of that, as a scientist, takes me from science into philosophy a little.
Well, we'll move swiftly back to science, then, Paul, in that case. But Phil, can I just continue what you were saying? This fusion process. So the fusion starts because of the force of the heat and the force of the compression. Mm-hmm. So the hydrogen fuses. Then what?
Well, the hydrogen fuses, it basically forms helium nuclei. Now, you may wonder, well, how do you get energy out of this process? It's not anything like the burning of hydrogen that we know on Earth. It's a completely different process. All you're doing is taking 4 protons and making one helium nucleus. But when you look at the mass of the helium nucleus compared to the mass of the 4 protons you put in, you discover you've lost something. You've lost just under 1% of the mass. And what happens to that? This is where Einstein's famous E equals mc squared equation comes in. That lost mass has gone into energy. So that's holding the star up against gravity. And that's exactly what's going on in the sun right now. Is
there any relationship between the length of life of a star and the size?
There's a very clear relationship. And it's a paradoxical one as well, in that the bigger a star is, the more fuel it has, the faster it burns it. And that's because it comes down to the conditions at the center of the star, which are required to balance it against gravity. Even the big stars are turning hydrogen into helium by almost the same process as I described. Bigger stars, those bigger than a couple times the sun, actually involve carbon, nitrogen, oxygen in a kind of catalytic cycle. But the end result is the same. But the star is so much bigger, it has to burn fuel that much faster. And in fact, it's roughly a star that's 10 times the mass of the sun will burn its fuel in only 1% of the lifetime of our sun. If you had been here, if we're talking about 1% of the age of the sun, instead of being a 10 billion year lifetime, we're looking at only 50 to 100 million years. So if you had been on the Earth at the time of the dinosaurs and looked at the night sky, the stars would have looked completely different than they do now.
Can we go back to the star itself, John Levin? What happens when a small star, Phil calls it, I do find all these numbers mind-boggling, but there you go. What happens when a small star, like the sun, runs out of hydrogen? What are the processes that go on? So there's this fusion. Mm-hmm. And can we just go right down the line there?
Well, after it burns up the hydrogen, when it first burns the hydrogen, it begins to make helium. And there will be a time when it's used up most of the hydrogen where it suddenly cools. And it no longer is giving off the energy from the fusion reactions, and so the star will begin to collapse. And as it collapses, it can cause another phase of burning in a kind of shell from the atmosphere that was left over. And then it'll distend. You'll get what's called a red giant, sometimes a red supergiant if it's a very massive star, or more massive than the sun.
Why do we call it red? Because of the colour? Obviously.
Well, yeah, because of the colour.
all right.
No, it's fair enough. And it distends. It can become quite enormous when the sun goes through this phase. It will blow out the entire solar system, essentially. It will swell and distend so large that that'll be the end of our living in the solar neighborhood in the comfortable conditions we're used to. And eventually, some stars will continue other phases of burning after that. You can have helium burning, carbon, what comes next? Oxygen, neon, silicon, magnesium, then silicon. Oh, my God. Yeah. I'm reaching back to my farthest memories here. And eventually you end up with iron in the core for very massive stars that can keep burning. Now, iron is very stable against fusion reactions, so it will stop at that stage.
Why does it get down to iron?
Well, it's really just the stability that you release energy with all of these fusion reactions until you get to iron. And if you continue to try fusion reactions, it will cost energy. So it's no longer energetically sensible to keep going in that direction. It will simply stop near iron. And you get these iron cores.
So big stars create the elements?
Big stars create, that is the most dramatic part of the story, is that the universe starts with very little in it but hydrogen and helium. And that's not a whole lot. You can't make life out of hydrogen and helium. You can't make water. You can't make planets. And it's not until after a first generation of stars that synthesize all of these elements reprocess them, blow them back out into the universe after they die, that you can have a second generation of stars, a generation of planets that can sustain water and atmospheres and ultimately life.
Yeah, it is amazing, isn't it? Can you just take us further? We have this periodic table so trippingly run through by Jana a few, few minutes ago.
I can't believe I remember the periodic
Never
table.
mind. So what happens then? So there they are, and then how does it get to be us, as it were?
Well, in fact, that's perhaps the most exciting phase of all in the evolution of stars.
We think so, maybe.
From our point of view.
From our point of view, you asked about the elements that make us. I mean, it's a wonderfully romantic notion that we are star children, but it's exactly true. But the heavy elements that we have on the Earth today, the iron and steel in this building, in the cars that you're driving in right now, they're not produced in stars like the Sun. They are produced in the heavier stars, stars bigger than about 5 or 10 times the mass of the Sun, which evolve quickly, as I've said earlier. And when they get to the end of their life, they've got all these very shell-burning phases in their core, which Jana described, in which the star is desperately searching all its energy reserves to try and keep itself up against the inexorable pull of gravity. I'm afraid that will eventually run out. Yes, it will reach the silicon burning phase. The amount of energy you get out of silicon burning is so tiny, the star can support itself for only a matter of days. So that's right at the end of its life. You've got the iron core. You can't get any more energy out of iron. The star starts collapsing. The temperature goes up even more. And curiously enough, the iron actually disintegrates, and the core goes into free fall, falling at actually something like a third the speed of light. The last phase is only about a second, until something odd happens, and the collapse stops because nature has one more arrow in its bow to stop the collapse. And it's a strange feature of quantum mechanics, which we only started to understand early in the last century, in which there's something called degeneracy pressure, in which you can't pack fundamental particles closer together than a certain distance. And it stops this collapse just dead from being something at a very high speed. And the material coming down, the rest of the star, literally bounces and produces a huge shock that comes back out through the collapsing star, heating it to tremendously high temperatures. But you've actually got all the ingredients you need in this process to manufacture. At this point, the star's given up. It's not looking for energy, and you can make all the elements, all the heavier elements than iron, up to lead, all the way up to uranium, in this process, which absorb energy. This we see as a supernova explosion, which you mentioned in the very beginning, the single most powerful cataclysmic event that we know in astronomy. That's where all the heavy elements get thrown back into space. That's where we come from.
Right. Paul, is this to do with... does this form what could be called a neutron star?
Yes, the lifetime of all stars depends on two structures: the core of the star and the envelope that surrounds it. The core is the place where the nuclear burning takes place. The envelope is what we see, and that core is what does the collapsing and creates a neutron star with everything packed together. The envelope is what's blasted off into space and gets bigger and becomes the supernova. And as Phil says, makes really heavy elements like gold and uranium. And when the core has collapsed to become a neutron star, perhaps a star with something like the mass of the Sun, but packed into a volume which is only 10 or 20 kilometers in diameter, so the whole star packed into something like the M25 orbital motorway. That is a star made of neutrons, and it's it's a stellar cinder. It's the end point of the evolution of very massive stars.
Jana, can we just talk a little bit more about the supernova. What happens when a star goes supernova? And there was one sighting, there are two sightings mentioned in the notes I got. One in 1054 by Chinese, Japanese and Indian astronomers. I'd very much like to know how they managed to sight what they saw. Was it near enough? And another was in 1987. Can you talk about those two? Because actually the 1054 one will bring in a sort of sense of the history of examination of the universe.
Well, supernovae are spectacularly bright. They can outshine the entire galaxy, of which they are just one member star. So if a galaxy has 10 billion stars, suddenly this one star will outshine the entire galaxy. So they're spectacularly bright. So one night you can look up in the sky and you don't see it, and the next night you suddenly do. They have pretty quick lives in the sense of how bright they shine. It can be months to years. 1987A, I think, took a couple of years to cool off before we couldn't see it that well anymore. So in 1987, it was in the southern hemisphere. I think it was in Australia. An astronomer looked up in the sky one day, and there it was, essentially. And that's quite spectacular. Those are rare events. We only see one in the galaxy about every century. And the last one that was visible to the naked eye was the one that you mentioned that was documented, particularly by the Chinese, as I remember. And I think it's now in Crab Nebula. That is a pulsar. It's a Crab Nebula. So that supernova is now a very famous neutron star. We now know how to look at, centuries later, build the telescopes to look out in the sky and see the cool remnant that we can no longer see with the naked eye. And it's a spectacular nebula, the gas left over from that explosion, and the core neutron star is there.
To go back to the discovery of the supernova of 1054, the Chinese courts, the imperial courts, hired astronomers. There was always in a forbidden city, in an imperial city, there was a quarter for the astronomers to live in, and there was a corps of officials, astronomers, whose job was to keep scanning the sky for signs of change and to interpret those changes for the benefit of the emperor. I mean, basically, they were looking out to warn him about things going on. And one of the key signs that they were looking for was the appearance of anything new, because that might herald, for example, an invasion. Somebody who wanted to overthrow, a cousin or a nephew who wanted to overthrow the emperor, that sort of thing.
Or a miraculous person.
Whatever. So there were observatories, which were kind of platforms raised high above the city, where astronomers would stand throughout the night, in fact, usually several of them, looking out for celestial portents. And so they developed quite sophisticated maps of the sky and immediately were able to notice where new things happened. And in 1054, on July the 4th, 1054, they identified this new star which had suddenly appeared, very noticeable to them because they had such good knowledge of where all the stars were, and wrote it down as a celestial portent, that there was a guest star, that it heralded possibly the arrival of an invader, and therefore the emperor should take the appropriate precautions. And they mapped looked at the brightness, the changes of brightness, specified the direction of the sky where it was, and all the rest of it. And these details come down to us in the imperial histories. Those imperial histories that survive the Mongol invasions contain these references to these guest stars that astronomers have mined for observations like this. Now, if you look in the same direction of the sky that the Chinese astronomers identified, you find this nebula called the Crab Nebula. It's a nebula which is rushing out from it in space in an explosion. If you track the explosion back, you find it was all accumulated together in 1054. So naturally, it's in the same direction. You've got the coincidence of space and time to identify this nebula with this imperial Chinese history.
Did the Chinese call it a guest star?
Yes.
Isn't it terrific? Guest star.
Yes, that's right.
Just visiting.
just visiting, that's right. But on a very cheap guest, too, because you didn't have to feed it.
And the ones in our galaxy as well, as Janice said, they're so bright that something like that is visible in the daytime.
Paul, sometimes a star collapses so far that it creates a black hole. Can we tackle that?
Well, if the core of a particularly massive star collapses, then even the destiny to be a neutron star is denied to it, because the material that it's trying to pack into being a neutron star is just too much, even for degeneracy pressure, as Phil mentioned, to hold it up. If the collapsing core is over maybe 2 times the mass of the Sun, then the neutron star actually can't stay up, and it has to collapse even further. And there is no state of matter which is known that will save it from this. The collapse creates a very, very small star indeed, with all of a large amount of mass packed into a tiny, tiny, tiny volume, less than a kilometre. And the force of gravity near such an immensely dense thing is so strong that not even light can escape from such a place. Light is a form of energy. Energy is responsive to gravity because of the curvature of space-time, as Janet mentioned at the beginning of our discussion. And the force of gravity in the vicinity of this thing has bent space so much that when light tries to travel along that space, it curves around and comes back to where it started. So anything that this object tries to emit never escapes, and that's called a black hole.
And this, John, I understand, gives off something called gravity waves.
Yeah, so...
Is that what Paul was alluding to towards the end of that?
Yeah, well, neutron stars can also give off gravity. Other objects can give off gravity waves, but black holes are probably the strongest source. As they collapse, or even if you have 2 black holes in orbit around each other, which can happen, a lot of stars are born in binary systems with 2 stars as opposed to 1, and they orbit each other. And as they evolve and die, you can form 2 black hole systems, or 2 neutron star systems, or a black hole and a neutron star. And as they orbit each other, the strength of the curvature of space-time around it is so strong, and it's trying to adjust as these objects swirl. It's like fish swirling in a pond. You get waves in the fabric of space itself. So space-time, the curves in space, wave through the universe. They emanate from these orbiting centers, or it can be caused by the collapse itself. And they emanate out through space relatively unimpeded, and then they pass through the Earth, and they're passing through the Earth right now. We're being squeezed slightly and stretched slightly. If you stuck your arm out and the wave was strong enough, you would see lengths being shortened or stretched. But it's so tiny, so imperceptibly tiny, that we simply can't see it. And the big ambition this decade is to build detectors both on Earth and in space that will be able to measure these minute deformations in the shape of space.
We've very little time, but just briefly, is there a possibility on your reckoning that the stars will go out, or there will be an end?
Eventually all the galaxies do disperse into space and stars fade away, and that's the end of it.
Can I just ask you for a little comment, Paul Murdin? I know it's ridiculous at this, but I'm fascinated by dark matter and dark energy. That's such wonderful phrases apart from anything else. Is there any progress being made on that? I mean, in a mere 500 million years' time, when they're having talk about in our time, will they be able to talk about dark energy and dark matter?
I hope so, yeah. I mean, there's a lot of effort going into trying to identify what the characteristics of dark energy and dark matter are, and to look at the effects of them. The dark energy concept has been around for 100 years, but it's only in the last, 5 years that there has been real evidence that it exists. Programs to try to understand the nature of it are ongoing. Yes, in 1 billion years' time, your descendant will be able to talk about it.
And I hope your descendants will come and talk about it too. Thanks all very much. And thank you very much for listening.
We hope you've enjoyed this Radio 4 podcast. You can find hundreds of other programmes about history, science and philosophy at bbc.co.uk/Radio 4.